In today's class and video, we are going to look at inhibition of acid phosphatase by inorganic phosphate. So we'll start our introduction by looking at what an enzyme inhibitor is. An enzyme inhibitor is a molecule that binds to an enzyme to decrease the activity of the enzyme. And the two main types of enzyme inhibitors are reversible inhibitors and irreversible inhibitors. And the main difference between the reversible inhibitors and irreversible inhibitors is that reversible inhibitors binds to the enzyme by forming non-covalent interactions, whilst irreversible inhibitors bind to the enzyme by forming covalent interactions. And basically, we have three main types of reversible inhibitors, and these are the competitive inhibitors or inhibition, non-competitive inhibitors or inhibition, and uncompetitive inhibitors or inhibition. For the competitive inhibition, the inhibitor binds to the active sites of the enzyme. And for the non-competitive inhibition, the inhibitor binds to the allosteric site of the enzyme. And for the uncompetitive inhibition, the inhibitor binds to the enzyme substrate complex. Now the next is enzyme inhibitor plot. So first of all, what we have to note is that enzyme inhibitor plots are graphs that show enzyme kinetics in the presence and absence of an inhibitor. They can be used to identify the types of inhibition and calculate for Km and V maximum values. And what we also have to note is that enzyme inhibitor plots are studied using the Michaelis-Menten plot or the Lineweaver-Berg plot, or both Michaelis-Menten and Lineweaver-Berg plots. So these are the plots on my left for the Michaelis-Menten plot, and also on my right for the Lineweaver-Berg plot. And basically what we have to notice is that these plots normally represent two main reactions in an enzymatic reaction. The first is the enzymatic reaction in the absence of an inhibitor, and which is indicated with the blue plot as seen over here for the Michaelis-Menten plot, and also seen here for the Lineweaver-Berg plot. And the second reaction, which is an enzymatic reaction in the presence of an inhibitor, which is also shown over here with this red plot for the Michaelis-Menten plot, and also for the Lineweaver-Berg plot shown here. And what we also have to note is that these plots basically tells us the relationship between the V maximum and the Km value for these two reactions based on the type of inhibition involved in the reaction. So let us now see how the three main types of inhibitors, that is the competitive, non-competitive, and the uncompetitive, affect the enzymatic reaction using the Michaelis-Menten plot or the direct plots, and the Lineweaver-Berg plot or the double reciprocal plots. So we'll start by looking at how the competitive inhibitor affects the enzymatic reaction. So if you are to take a look or study the direct plots over here, we can see that the V maximum for both reaction, that is the reaction without the inhibitor and the reaction with the inhibitor, which is indicated as I over here, is the same. And also there is also an increase in the Km value for the reaction. So we can say that V maximum is unchanged, that is remains the same, and there's also an increase in the Km value over here for the Michaelis-Menten plot for the competitive inhibition. If we should also look at the same inhibition for the double reciprocal plots, we can also see that there's an increase in the Km value over here as shown over here. The V maximum is also unaffected. That means the V maximum remains the same. There is also a change in the slope and the y-intercept for both reactions. So that is the reaction with the inhibitor and without the inhibitor also remains the same as shown over here. So now let us look at the non-competitive inhibition or inhibitor. So if you have to look at the direct plot, so we can say that there's a decrease in the V maximum, and also the Km value remains the same for the non-competitive inhibition for the Michaelis-Menten or the direct plot. If we should also look at the same type of inhibition for the double reciprocal or the line reversible plot, we can see that our Km is unaffected, or in other words, the Km remains the same. The V maximum is also reduced over here as shown here. The slope also changes and the y-intercept also changes from this plot. And if you are also to look at the uncompetitive inhibition from the direct plot, we can see that both V maximum and the Km are being reduced. So from the plot over here, so this is our V maximum, which is being reduced from here to here, and this is also our Km, which is being reduced from here to here. And for the double reciprocal plot, we can see that the Km is still reduced over here. The V maximum is also reduced. The y-intercept also changes, but the slope for these two reactions remains the same. And this is indicated by the two parallel lines seen over here. Now let's look at inorganic phosphate inhibition on acid phosphatase. So first of all, what you have to note is that inorganic phosphate competitively inhibits the hydrolysis of p-nitrophenol phosphate by acid or alkaline phosphatase. And once this inorganic phosphate competitively inhibits the reaction, this is the nature or the plot for the line reversible plot that is expected after performing our experiment. So let's now look at our test protocol for our experiment, and we start by looking at the materials needed. So we have acid phosphatase, we have 0.025 molar p-nitrophenol phosphate, we have 0.05 molar sodium phosphate of pH 4.8, 0.1 molar citrate buffer pH 4.8, water bath set at 37 degrees Celsius, 0.1 molar sodium hydroxide, and a UV spectrophotometer set to 405 nanometer. So next is to look at the test method. And the first method is the substrate buffer preparation. And to do this, we prepare a series of 5 test tubes as shown over here, with the first containing 0.05 ml, the second 0.1 ml, the third 0.2 ml, the fourth 0.5 ml, and the fifth 1 ml of our 0.025 molar PNPP, which is our artificial substrate. So the next step is to add to each test tube 2 ml of our 0.1 molar citrate buffer as shown over here. The next step is to add 0.2 ml of the inhibitor, which is the 0.05 molar sodium phosphate to each test tube, and also shown over here. The next is to top up to a volume of 4.5 ml with distilled water. And to do this, for the first test tube, we add 2.25 ml of distilled water to get a final volume of 4.5. For the second test tube, we add 2.20 of distilled water to get a final volume 4.5. For the third test tube, we add 2.1 ml water to get a final volume. For the fourth test tube, we add 1.80 ml of the distilled water to get a final volume. And for the fifth test tube, we add 1.3 ml of distilled water to get a final volume of 4.5 ml. So once we are done with the substrate buffer preparation and the addition of our inhibitor, the next thing to do is to dilute our enzyme. So we prepare 5 ml of the following dilutions from the stock acid phosphatase. So that is 1 in 10, 1 in 100, and 1 in 1000. So to do this, to prepare the 1 in 10 dilution, we pick from our stock acid phosphatase 0.5 ml and add to 4.5 ml of distilled water to prepare our 1 in 10 dilution. To prepare the 1 in 100, we pick 0.5 ml of our 1 in 10 dilution and add to 4.5 ml of distilled water. And to prepare our 1 in 1000 dilution, we pick from the 1 in 100 dilution 0.5 ml and add to 4.5 ml of distilled water. The next method is to equilibrate both the diluted enzyme and the substrate at 37 degrees Celsius for 5 minutes in a water bath set at 37 degrees Celsius as shown here. And what we also have to note is that the tube of the diluted enzyme as well as the substrate buffer here represents the rest of the tubes for this experiment. So the next is to perform our substrate enzyme reaction or to perform our reaction mixture. And to do this, after the 5 minutes of incubation, we add 0.5 ml of the equilibrated diluted enzyme to our 4.5 ml substrate buffer in a water bath at 37 degrees Celsius. So right after adding the 0.5 ml of the equilibrated enzyme to it, we mix and immediately remove 1 ml sample from the reaction mixture and add to a different test tube containing 5 ml of 0.1 molar sodium hydroxide. And the role of the sodium hydroxide over here is to stop the reaction. So we take this as 0 time or control against the rest of the incubation that we will be doing. So we repeat step 8 at 10 minutes and 20 minutes intervals for each tube. So at 10 minutes, we pick 1 ml from our reaction mixture in the water bath and add to 5 ml of sodium hydroxide contained in a different test tube. And also at 20 minutes, we pick 1 ml from the reaction mixture in the water bath and add to a different test tube containing 5 ml of 0.1 molar sodium hydroxide. So we then measure the absorbance for the 10 minutes and the 20 minutes incubation respectively at 4:05 using the 0 minute as a blank. So this is our assumed table of result for the 1 in 10 dilution. So from the table, we can see this is the volume of our p-nitrophenyl phosphate, which is our artificial substrate used for the reaction, and this is the volume of the buffer added to each of the test tube, and this is the volume of water added and the volume of our inhibitor added to each substrate buffer. And these are the obtained absorbance values at 10 minutes and also at 20 minutes respectively. So let's now see how to determine the moles of p-nitrophenol hydrolyzed from our PNPP at 10 minutes of incubation using the p-nitrophenol calibration curve. So first of all, what you have to note is that this is our calibration curve over here for the p-nitrophenol, and the equation of the line is giving us y equals 6.7318 s, where y happens to be the absorbance value on the y-axis and the s happens to be the moles of p-nitrophenol on the x-axis of the calibration curve. So if you want to determine the moles of p-nitrophenol hydrolyzed at the 10 minutes of incubation, we make S the subject from the equation of the line and substitute Y with the absorbance value that we obtained for each of the reaction at the 10 minutes of incubation. So let's just give a try for the moles of p-nitrophenol hydrolyzed for the first reaction in the first test tube. So we will just have to make S the subject, and to make S the subject, we will get S is equal to Y divided by the slope over here. After this, we then substitute this absorbance value over here into the equation. So if you are to do this, we will get 0.034 divided by 6.7318. And if you have to calculate this, you get 0.051 micromole. But what we also have to note is that, and this is very important, we use a 1 in 10 diluted enzyme. So to determine the actual moles of p-nitrophenol hydrolyzed by our enzyme at the 10 minutes of incubation, we will have to multiply the obtained moles by our dilution factor, which is 10. So as you can see over here, so we are saying that DEF times the mole determined from the calibration curve. So this will be equal to 10 times the 0.0051 micromole obtained over here, and this will be equal to 0.051 micromole. So this is the actual moles of p-nitrophenol hydrolyzed by our enzyme at the 10 minutes of incubation. So if we should take a look at the table over here, for the second reaction, so this is the actual moles of p-nitrophenol formed, we have 0.074. For the third reaction, this is the actual moles of p-nitrophenol formed. For the fourth reaction, so this is the moles of the p-nitrophenol formed. And for the fifth reaction, this is the moles for the p-nitrophenol formed. So now let us calculate the reaction velocity for each of the reaction. So given that the reaction velocity is equal to the moles of p-nitrophenol formed divided by the moles of the reaction mixture and the time for incubation. So to do this, we know that for the first test tube, the moles of p-nitrophenol formed is 0.05. For the second test tube is 0.074. The third test tube is 0.085. The fourth 0.201, and the fifth test tube is 0.263 as shown in the table here. So to calculate the reaction velocity for the first reaction in the first test tube, we put the moles of p-nitrophenol formed over here, then we divide it by the volume of the reaction mixture, which is 5 mL, times the time for incubation, which is 10 minutes. So the first test tube, if you have to do the calculation, we'll get 1.02 times 10 exponent negative 3 micromole per ml per minute. For the second test tube, so if you are to put the moles over here into the equation, we will get 1.48 times 10 exponent negative 3 micromole per ml per minute. So for the third test tube, if if you are to do the calculation, we will get this value. For the fourth test tube, we will also get this value, and for the fifth test tube, we will also get this value over here. But for one thing we also have to notice that for us to plot the line reversible plot, we always plot our 1 over V against our 1 over the substrate concentration. So what it means is that we will have to convert this the reaction velocity over here. We will have to divide each of the values over here. So if you are to do this, it will be 1 divided by this value over here. So if you have to calculate for this, we'll get 980.4, and 1 divided by the reaction velocity value here will give us 675.7, and 1 divided by the reaction velocity value over here will give us 588.2. 1 divided by this will give us 248.8, and 1 divided by the 5.26 times 10 to the negative 2 will also give us 190.1. So this is just a table showing the test tubes and the moles of P nitrophenol formed in each reaction, and the reaction velocity, and the 1 over V values for the reaction. So the next is to calculate for our substrate concentration for each of the reaction. So first of all, let us take a look at the table over here. So for the first reaction contained in the first test tube, so this is the volume of our PNPP used. For the second test tube, this is the volume of our PNPP used. The third test tube, the volume of our PNPP used. The fourth, this is the volume, and the fifth, this is also the volume of our PNPP used. And this is the concentration of the PNPP used throughout the reaction, which is 0.025 molar. And this is the final volume for our substrate buffer, which is 4.5. And to do this, we also have to use the equation C1V1 equals C2V2 and make C2 the subject. So which is the substrate final concentration in each of the reaction. So making C2 the subject, we will get C1 V1 divided by C2 divided by V2. So let's see the substrate concentration for each of the test tubes. So for test tube 1, we know our C1 is 0.025, and the volume of PNPP used is 0.05 as shown in the table here, and our V2 is 4.5. So if you have to do this calculation, we'll get 2.78 times 10 exponent negative 4. If you have to do the same for the second test tube, you'll get this value. For the third test tube too, we also get this value. For the fourth test tube, you'll get this, and for the fifth test tube, you will also get this value. So when we are done with this, we now find the 1 over S value by taking the inverse by dividing this value as shown over here. So if you have to do this, we will get 1 over this value, and if you have to calculate, we will get this result. And if you also to take 1 divided by the substrate concentration over here, we will get this result. And if you have to do 1 divided by the substrate concentration, we will get this result. And if you have to solve for this, we will also get this result. And if you have to also to solve for this, we will also get this result. So this is just a table showing the 1 over the substrate concentration values and the 1 over the V values for the two reactions. So the first table shows the values for the reaction in the presence of an inhibitor, and the second table also shows the 1 over S and the 1 over V values for the reaction in the absence of an inhibitor. So we then plot these values on the same graph, and if you are to do this, This is the nature of graph that we are going to get over here, and this is the reaction without inhibition, or in the absence of an inhibitor. And this is also the graph showing the reaction in the presence of an inhibitor. And if you should look at this, both the two reactions has the same intercept on the y-axis. So, and this is the equation for the reaction in the presence of an inhibitor, which is giving us y equals 0.2397 s plus 187.75. And this is also the equation of the line for the reaction in the absence of an inhibitor, which is also giving us y is equal to 0.0938 s plus 187.75. And if we should also look at our axis, on the y-axis, we have our 1 over v values, and also on the x-axis, we also have 1 over the substrate concentration values. So I'll just leave you with these questions, and I'll advise you meet as a group and discuss these questions. And I also encourage you to understand the questions and calculate them very well before you come into the lab.